Okay, so in this video we'll be solving an HMMT problem. And this HMMT problem follows Max, who for some reason goes out into a hurricane and starts flipping coins and recording results because he's insane. And so the way that the problem goes is that every time he flips a coin, the coin blows away with probability 4%. And otherwise he records the result as heads or tails. Now once a coin gets blown away, he obviously can't flip it anymore. And so the question asks that once it gets blown away, what's the expected value of the difference in the amount of heads and tails? So we're looking for the expected value of the absolute value of h minus t, where h counts the number of heads and t counts the number of tails that he writes down. So one approach to this problem is to use a generating function. And so why is that a nice approach? Well, the probability that he flips it exactly n times is gonna be some probability associated with some sort of geometric looking like series. And expected value with that sort of probability plays really nicely with generating functions, as we'll see in a moment. So what we'll create is, as usual, some function f of x, which is equal to a1 x to the power of 1 plus a2 x squared plus a3 x cubed, and so on and so forth. And so what do these an represent? Well, we want something that's indexed by the integers, so we can count how many flips he has made. So an counts the expected value of this quantity that we're looking at, h minus t, given exactly n flips. Now, how can this help us solve the problem? Well, notice that the probability that he makes one flip is 0.96 times 0.04, because he makes one successful flip, which happens with probability 0.96, and then the next one gets blown away, which happens with probability 0.04. And then for two flips, it's 0.96 squared times 0.04, because it's 0.96 for the first toss, 0.96 for the second toss, and then 0.04 that gets blown away on the third one. And similarly, for exactly three tosses, 0.96 cubed times 0.04, and so on and so forth. And so the expected value is, the expected value in total is the expected value for given exactly n flips times the probability that it makes exactly n flips. So if we now look at the quantity 0.04 times f of 0.96, notice what happens here is that this term becomes 0.96 times 0.04, this one becomes 0.96 squared times 0.04, this one becomes 0.96 cubed times 0.04, and that is the probability that he makes exactly n flips, and we're multiplying that by this expected value given that he makes exactly n flips. And so that'll give us exactly our expectation value that we're looking for. So now another thing that you might ask is, why aren't we counting for zero flips? Well, for zero flips he doesn't write down anything, so that's zero anyway, so you can just ignore that. So now let's calculate what a sub n should be. So given that we have exactly n flips, we can rephrase this problem as saying, like, say we have n blank spots, and we have some sequence of tails and heads. So like, for example, we can have this, and this has one more heads and tails, so the value will be 1. So we can phrase the problem as saying, okay, let's say that we have k tails and n minus k heads. So what's the value of h minus t? Well, that'll just be absolute value of n minus 2k, because you're just taking the difference of these two values. And so you want to calculate that times the probability that, for example, here you have 3 heads and 2 tails, and you multiply that by the probability that you have 3 heads and 2 tails, and multiply that by this quantity, which will be 1, and sum that up for all possible combinations of k tails and n minus k heads. So notice that this takes on two values. If n is less than or equal to 2k, then this will become 2k minus n, and if n is greater than or equal to 2k, then this will be n minus 2k. So notice that there's a symmetry that if we have 3 heads and 2 tails, that's really saying the same thing as if we had 3 tails and 2 heads. Because you have one more of one than the other one, and here we're just looking at the absolute value of their difference. So instead we can rephrase this as saying split up into two cases where you have more heads and tails or more tails and heads, and you can look at the expected value in one of the cases and then multiply it by 2 because you have a symmetric thing in the other case. So what we can do is we can say that the expected value a sub n is equal to 2 times the sum from k equals 0. Now here's where it gets a bit tricky. If n is odd or even, you have two different cases, because if n is even, then you're counting the case for, say n is equal to 6, you're counting the case for 3 heads and 3 tails twice in what we're about to do. But if n was odd, then there is no half case that you have to worry about. So for right now, I'm going to work with n being odd. And so in this case, for example, all the ways that you can have more heads than tails is saying that you have 0, 1, or 2 tails, which will amount to the corresponding number of heads. And 0, 1, or 2 tails corresponds everywhere from k equals 0 to k equals n minus 1 over 2. And now we want to have the value that we're looking for, which is the absolute value of h minus t. And so that'll just be the absolute value of n minus 2k. But this is positive from k equals 0 to n minus 1 over 2. So that'll just be n minus 2k. And then we want the probability that you will have k tails and n minus k heads. So because there are n positions and k places to put the tails, that'll just be in n choose k. And then you want the probability that you get k tails, which is 1/2 to the power of k. And then the probability that you have n minus k heads, which is 1/2 to the power of n minus k. Now we can combine these two. Notice that this is just 1/2 to the power of n. But we can also bring that to the outside and cancel it with the 2 and change this bit to being 1 over 2 to the power of n minus 1. Now, this is some sum involving binomial coefficients, and we can worry about this constant term later. So a nice common thing that you want to do when you're trying to take sums of binomial coefficients is look back to the binomial theorem and try to find some generating function methods to do that. And this problem is quite nice because there's a nice little trick that you can use to sum up values of a generating function, and that algebraically happens to cancel out nicely with another part of the generating function that you'll have. So let's try to create a generating function which looks like sum from k equals 0 to n of n choose k times n minus 2k times x to the power of k. So this sort of, I want some generating function which has these coefficients times x to the power of k. And because we know like the binomial theorem, it makes more sense to go from k equals 0 to n because that's probably going to be something easier to find. And then we want to sum up the coefficients of these from k equals 0 to k equals n over 2, the coefficients of x to the k. So first let's find out this generating function. Well, we can start off with 1 plus x to the n, which is sum of n choose k to the k from k equals 0 to n. And so we want to modify this to get an n and a minus 2k here. So to get an n, what we can do is we can just multiply both sides by n, so that's not too tricky. To get a minus 2k, what we can do is we can differentiate both sides. And then we get n times 1 plus x to the power of n minus 1. And this will be equal to the sum from k equals 0 to n. By differentiating term-wise, you get this is n choose k times x to the power of k minus 1. Okay. So this almost looks like this minus 2k x to the power of k, but this has a k minus 1 here. So what we can do is we can multiply both sides by x and get rid of that minus 1. And then since we want a minus 2k, we can just multiply this by negative 2, and this will become a minus 2 times k. And how do we change this into looking like n times that? Well, we can just multiply both sides by n. And so now if we add up both of these equations, we get that n times 1 plus x to the power of n minus 2n times 1 plus x to the power of n minus 1 times x is going to be equal to the sum from k equals 0 to n of n choose k times n minus 2k times x to the power of k. Okay, so this left side seems like we can factor out some stuff and simplify it a bit. So let's write that out. N times 1 plus x, power of n minus 1. Because we notice that that appears in all the terms. And then here from the left side we have a 1 plus x. And then from the right side we have a 2x remaining, so that's minus 2x. But then we can cancel that out a bit and rewrite this as being 1 minus x. Okay, so let's say that in general we have some generating function which looks like, I don't know, b1 or b0 plus b1x plus b2x squared and so on. And we want to sum up the first couple coefficients of this. Well, how can we do that? Well, one clever trick that you can do is multiply this by a series 1 plus x squared and so on. So let's look at what the coefficient of x to the 0 is going to be. So something times x to the 0. Well, the only way that you can get x to the 0 is by multiplying b0 times 1. So it'll be b0. Now let's look at, we'll have something times x2 first. Well, here you can multiply 1 times b0 and then b1x times 1. So that'll be b0 plus b1 times x. Now let's look at the coefficient of x squared. Well, here you can multiply x squared times b0, or x times b1x, or 1 times b2x squared, and you'll get b0 plus b1 plus b2 times x squared, and so on and so forth. So hopefully you see the pattern that the coefficient of x to the n here is the sum of the first n terms of this series. And notice that this series on the right converges to 1 over 1 minus x times whatever function you have out there. So we can do the same sort of trick here, where we multiply this function by 1 over 1 minus x. And then we look for the coefficient of here. We want to take the sum up to n minus 1 over 2, so we look at the coefficient of n minus 1 over 2 here. Okay, so let's do that. Let's divide this through by 1 minus x, so those two will cancel. And what we're left with is n times 1 plus x to the power of n minus 1. Now since we're looking for the coefficient of n minus 1 over 2, we can just use simple binomial theorem, and that'll tell us that this is n times n minus 1 choose n minus 1 over 2. And we can now reintroduce that 2 to the power of n minus 1 here. And we can write this out as being n times n minus 1 factorial divided by 2 to the power of n minus 1. This is n minus 1 over 2 factorial squared. And remember, here we're only taking into account that n is odd, so n minus 1 over 2 is going to be an integer. First off, notice that here it's n minus 1 over 2 squared because n minus 1 n minus 1 minus n minus 1 over 2 is n minus 1 over 2. So that's just the binomial theorem. And in this numerator, we have an n times n minus 1 factorial. We can just simplify that to an n factorial. And in the denominator, we have something that looks like this. So let's try and simplify that out a bit. So let's say that we have 2 to the n minus 1 times n minus 1 over 2 factorial squared. So this will be 2 to the n minus 1 times n minus 1 over 2 times n minus 3 over 2 times n minus 5 over 2 all the way down to 1, and then you're squaring all of that. So how many terms do we have here? Well, we have here n minus 1 over 2 terms, but then you're squaring that, so in total you have a copy of each one of these. So that will mean that you have n minus 1 total terms. And notice that we have n minus 1 2's over here. So we can distribute that into this. And each coefficient here gets 1, 2. So this will change that to an n minus 1. This will change that to an n minus 3. This will change that to an n minus 5. And it'll go all the way down to 2. So this will look like n minus 1 times n minus 3 times n minus 5 all the way down to 2. And that has some notation. That is called n minus 1 double factorial, all of that squared. And so what double factorial means, it's not taking the factorial twice. It's saying that if you have an odd number, you say like 5 double factorial, then you keep subtracting 2 until you get 1. So it's 5 times 3 times 1. Or if you have an even number, like 8, then you keep subtracting 2 until you get to 2. So it's 8 times 6 times 4 times 2. And so here, what this means is that this term is equal to n minus 1 double factorial squared. It's equal to n factorial over n minus 1 double factorial, all of that squared. And you can verify something, that n factorial over n minus 1 double factorial is actually just equal to n double factorial. And so the way you can think about this is, for example, here n is odd, so this numerator is going to have odd and even numbers. This n minus 1 double factorial will cancel out all the even terms, and then all you have is all the odd terms, which will give you n double factorial. So we can rewrite this as n double factorial over n minus 1 double factorial. So that is your value of an for n is odd. And I'll leave it as an exercise to you. You can try it out in much the same manner as we had here. To check that for n is even, we have that an is equal to n minus 1 double factorial over n minus 2 double factorial. And so one thing that you may concern yourself with is, in this case, we're just counting the terms from k equals 0 to n minus 1, and then using a symmetry argument to say that there is another case exactly like that where you have more tails than heads. However, for the case where n is even, then the case when k equals n over 2, you're double counting that because you have the exact same number of heads and tails, so you're counting that in both cases. But that's actually fine because the value of n minus 2k ends up being 0. So you can try this algebraic manipulation and see that you get these values for n is even. So with that, I'll clear up the board and then get to evaluating this generating function. Okay, so recall that we are trying to find this expectation value of the difference between the number of heads and tails that Max flips in this hurricane. And we determined that that was going to be equal to 0.04 times f of 0.96, where f of x is equal to this generating function. And so the a sub n are this expectation value of the difference in the number of heads and tails when he gets to flip exactly n coins. And so using another generating function, we figured out that a sub n is equal to n double factorial over n minus 1 double factorial if n is odd, and n minus 1 double factorial over n minus 2 double factorial if n is even. So remember that n double factorial is n times n minus 2 times n minus 4. And you just keep multiplying those numbers going down by 2 until you get to 2 or 1. So that doesn't exactly make it clear what 0 double factorial should be, but 0 double factorial should be 1. You can explain that either by saying it's the empty product or by just noticing a pattern that has to make it work. And so, try it out a bit more explicitly. We can say that f of x is equal to 1 double factorial over 0 double factorial times x plus x squared, because notice that if you have x here, then that'll be 1 over 0. And if you have n equals 2 here, then that'll be also 1 over 0. And for 3 and 4, similarly, it's 3 and 2. And over here, for 4, it's also 3 and 2. So you can group them together every 2. So you end up with this term, 3 over 2 times x cubed plus x to the 4th, 5 over 4 times x to the 5th plus x to the 6th, and so on and so forth. Okay, so now we want to evaluate what this is and then use that to figure out and finish our problem. Now, you might notice that this is a bit of an awkward generating function because you have every 2 consecutive terms have the same exact coefficient. So one thing you might think about doing is saying, okay, we can factor out this x plus x squared. And what are we left with? 1 double factorial over 0 double factorial times x to 0 plus 3 over 2 times, so this is x cubed and this is x for the smaller term, so this will be x squared. And then 5 double factorial over 4 double factorial times x to the 4th by the same reasoning, and so on and so forth. And this seems a bit more natural because the exponents here sort of seem to be the same thing as the denominators here. And so we can compute out what this generating function is and then use that to figure out f of x. So let's give this guy a name, let's call it g of x. Okay, straightforward enough. So now how do we compute g of x? Well, if you think about methods of computing infinite generating functions, I guess, the most basic example is 1 plus x squared plus x cubed and so on and so forth. So how do you do that? Well, you multiply everything by x, then you subtract them off and notice most of the coefficients cancel out and you get left with 1. And that gives you that your final generating function is 1 over 1 minus x. So here what we can try and do is find out some relation between consecutive coefficients and then try to use that to simplify our problem and get some relation on g of x, which will give us our answer. So let's try and look at, for example, 3 double factorial over 2 double factorial, and inspired by the other generating function, we might think about subtracting the next term, 5 double factorial or 4 double factorial, or doing something like this. Now, if you naively try to simplify this, you can multiply these two, so that'll give you 3 double factorial times 4 double factorial, which will be 4 factorial by what I said earlier. And here you have 2 double factorial times 5 double factorial, and that's a bit more complicated. And in the denominator, you have 2 double factorial times 4 double factorial, and that's even more complicated, especially as the terms grow larger and larger. But you might notice that you don't actually need to multiply out everything, and you can actually use this rule that n plus 2 double factorial is equal to n plus 2 times n double factorial. So this is basically because you multiply every other term until you get down to 2 or 1. And so, for example, 6 double factorial is 6 times 4 times 2, and 8 times that is 8 times 6 times 4 times 2, which is the same thing as 8 double factorial. And so this is analogous to n plus 1 factorial equals n plus 1 times n factorial. Okay, cool. So that being said, you can multiply the denominator and numerator by 4. And so this thing becomes 4 double factorial. So, okay, that's nice. That'll be the same denominator as this. And by the same token, this is 5 times 3 double factorial. And so notice that here you can factor out 3 double factorial and maybe you work something with that. Okay, so inspired by that choice, we might want to try and either increase the denominators here or decrease the denominators by 2 so that we can try and cancel some stuff out. So the easiest way that you can do that is by noticing like, hey, look, the exponent is the same as the denominator. So if we take the derivative of this function, maybe we can get something useful. So let's look at what g prime of x is. Well, the first term you can ignore because it's x to the 0. The next term will look like 3 double factorial over 2 double factorial times 2 times x to the 1 plus 5 double factorial over 4 double factorial times 4 times x cubed, and so on and so forth. So let's look at this term. Well, if you isolate the n double factorial, you realize that n double factorial equals n plus 2 double factorial over n plus 2. So what that means is that you can sort of multiply numerator and denominator by a half, and then cancel this 2 double factorial down to the one that's 2 less than it, and that becomes a 0 double factorial. Similarly here, you can sort of cancel out the 4s, and then that will become a 2 double factorial. Maybe this more cleanly. And if we look at the next term, what should that be? Well, you should be able to add 2 to everything, so that should be 7 double factorial over 4 double factorial times x to the 5th, and so on and so forth. And let's see if this makes sense. So it'll usually be 7 over 6 times x to the 6th, but then when you take the derivative, the 6's cancel out, and then you're left with 7 over 4. Okay, cool. So now, let's try and match our coefficients here. Notice that these denominators are the same, but the exponents are a bit different. So we can remedy that by looking at x times g of x. So what will this be equal to? Well, this is 1 double factorial over 0 double factorial times x to the power of 1 plus 3 double factorial over 2 double factorial times x cubed plus 5 double factorial over 4 double factorial times x to the 5th, and so on and so forth. Okay, cool. Now these guys have the same denominators and the same exponents on x, so we can subtract the 2. And if we subtract this from that, what we end up with is 3 double factorial minus 1 double factorial. Now notice that 3 double factorial is 3 times 1 double factorial. And so we can factor out the 1 double factorial, and what does this become? It will become 1 double factorial times 3 minus 1, or 0 double factorial times x to the 1st. Plus, similarly here we can factor out 3 double factorial because 5 double factorial is just 5 times 3 double factorial. And this will be 5 minus 1 over 2 double factorial times x cubed plus 5 double factorial times 7 minus 1 over 4 double factorial x to the 5th, and so on and so forth. Okay, so let's see what these come out to be. This will be 2, this will be 4, and this will be 6. Now we run into something that's a bit more tricky, but notice that these terms are 1 more than the exponent. So it almost seems like you have something that looks like n times x to the n minus 1. So this almost looks like it's the derivative of something. So let's see what that something would be. So this is d by dx of 1 double factorial over 0 double factorial, where we're going to increase the exponent by 1 and get rid of this 2 there, so that'll be x squared. And then 3 double factorial over 2 double factorial. And get rid of the 4 and increase the exponent, so that'll be x to the 4th, and so on. X to the 6th, and there. Okay, so these coefficients look familiar. They're original function, except notice the exponents are increased by 2. So what this will be d by dx of our original function g of x times x squared. And now we can apply our product rule to this and say that this is equal to g prime of x times x squared plus 2x times g of x. Okay, so what have we now concluded? If we write this big equation down, we have g prime of x minus 2x, minus x g of x is equal to g prime of x times x squared plus 2x g of x. So now let's isolate g prime of x on one side and g of x on the other side, and you end up with g prime of x times 1 minus x squared is equal to 3x g of x. Now we want to sort of isolate everything with g of x on one side and x on the other side, and so that becomes g prime of x over g of x. and this right side is equal to 3x over 1 minus x squared. So that doesn't seem too bad. This left side you might recognize as being some sort of derivative of a logarithm, so this will be the derivative of log of g of x. And this right hand side, you can play our favorite game of integration by guess and check. And this sort of seems like 1 minus x squared in the denominator and an x in the numerator, which is x1 less than x squared. So this will be something times the log of 1 minus x squared. Because if you take the derivative of this will be negative 2x over 1 minus x squared. So all you need to figure out is the factor up front. And you can pretty easily see that that should be negative 3 over 2. So this says that log of g of x is equal to negative 3 over 2 log of 1 minus x squared plus some constant. So what should this constant be? Well, let's plug in x equals 0. So on the right side here we have log of 1, which is 0. The left side here we can look back at the original generating function. And where is g of x? Yeah, so this part is g of x. And so if you plug in x equals 0, all these terms will be 0. 1 double factorial over 0 double factorial is 1. And you have x to the 0. So this thing will also be log of 1, which will be 0. So c equals 0 minus 0, so c is just 0. So we can just ignore that bit over there. Okay. So what are we left with? Well, if you exponentiate both sides, we get g of x is equal to e to the power of negative 3 halves log of 1 minus x squared. However, you can rewrite this as being e to the power of log of 1 minus x squared to minus 3 halves. So you finally get that g of x is equal to 1 minus x squared to the power of negative 3 over 2. Okay, that was quite a bit of computation, but we finally figured out what that is, which means that we can plug in that value to figure out what our function or what our expectation value should finally be. Okay, so we know that f of x is now equal to x plus x squared times 1 minus x squared to the power of negative 3 halves. And now we want to do this computation over here. So I did not actually ever do the computation, I just looked at the answer key. But let's see if I can do it out right now. So we're looking for 0.04, which is 1 over 25, times, well, x plus x squared, you can just factor that out as x times 1 plus x. So I guess you can write that out as 24 over 25 times, it's 0.96 plus 1, so that'll be 49 over 25. And then 1 minus x squared. So that'll be 25 squared minus 1 over 25 squared power of negative 3 halves. So then this numerator I want to say is equal to 24 times 26. And here in the denominator you get a 25, so that will cancel out. And you get 25, which cancels out with the square root, and then you get a cube. And then because this is to the negative, you get 25 cubed, and those 25 cubed will cancel out these. So this will be 24 times 49 times 1 over 24 times 26 to the power of 3 halves. Not quite sure if that's correct, but the answer should come out to 24 over 7. So if you want, you could check out if that is, if my math is correct, but that should be the answer to this problem. Okay, so this is supposed to be 24 squared. And so what that comes out to be is using difference of squares. This will be 49 times 1. And so what this will just be is 49 to the 3 halves. And so what happens there is you end up with a 7 cubed. And so that 7 cubed will cancel out with that 49, and you're left with 24 over 7. So there you go. That's the answer.